Hello and good afternoon, everyone. I welcome you all to India's largest e-learning platform, Unacademy. And I welcome you all to my session of Antenna CTQ series. I welcome you all to the Gate Conqueror channel. We are into Antennas Concept through Question series. And this is part 7. How are you all, dear? Yes. Before we start the class, let me introduce myself. I am G Reddy. Someone please confirm the video and audio once. Just confirm the video and audio once. That must be good, I think. Video audio good. Just let me know. Yeah, fine. So I have a total 15 plus years of experience in teaching, guiding and mentoring GATE and ESE aspirants. Worked as motivational speaker pan-India for the past 12 years. Expert in field theory and communications. And this is the official link. You can join us on Telegram. The advantage of joining us on Telegram is that you can get a personal level support from all the faculties of the GATE Conqueror team. As you know, the good thing is recently 4 new educators added into our team. Now we are a total of 4 plus 4, 8 educators for this English speaking channel. And we are determined cover GATE 2023, Engineering Services 2023 comprehensively this time. We have sufficient resources to do so, and I take the responsibility to complete EMFT and communications comprehensively for GATE 2023 for ECE and to complete EMF for GATE and ESE 2023. This is also GATE 2023 and ESE 2023, EMF, GATE and ESE 2023 for electrical. I have to be covering advanced communications, ESE 2023 for ECE people. So this is what I am trying to plan here. In this is already done. A playlist for this is also created. This task is done, and this task is done around 60%. Advanced communication I explained in app or special classes. We need to finish it off on YouTube. Clear? what we covered in EMFT, I'll try to explain here. Before that, let us see what are the paid subscriptions that are offered by Unacademy. Unacademy offers two paid subscriptions. One is Plus subscription, other is Iconic subscription. In Plus subscription, you got to have the face time of legendary faculties in the form of live classes, weekly test, structured courses, unlimited access, rank improvement batches, and crash courses. In Iconic, you have all these features. Along with that, you have a personal coach for one-on-one guidance, dedicated doubt clearing educators to clear your doubts, preparatory study material, personalized test analysis, study booster sessions, and study planner. If you are going for Plus subscription or Iconic subscription, I recommend you to go for a no-cost EMI. No-cost EMI is a case where total cost will be divided by number of months without any extra charge. Moreover, you can use our code KNR10 to get additional 10% off the year. With Iconic subscription, you get 1:1 live mentoring, increasing your chance of getting a top rank. With GATE and ESE Iconic subscription, you'll get a personal coach for 1:1 live mentoring, online study material, priority in Ask a Doubt, live doubt solving sessions, study booster sessions, priority in live classes using raise hand option, open house sessions with educators, community learning, and all the advantages of Plus subscription. Take an Iconic subscription to take your preparation to the next level and crack the exam. There is an offer for Plus subscription. With every 12-month Plus subscription, we are giving away 2 months extra subscription free for campus placement and IT jobs. It can be used for GATE and ESE preparation. With every 24-month subscription, we are giving away 3 months subscription free for GATE and ESE preparation. Offer is valid till April 14, 2022. You can subscribe using our code KNR10. Hello Anil, good evening. Free physical notes for GATE Iconic 1 year and above subscribers. Curated under mentorship of top educators. Comprehensive syllabus coverage. Solved examples to build problem solving skills. Available for electrical, EC, mechanical, civil and computer science. And these physical notes will be dispatched from last week of May. And these physical notes are designed and curated by India's top educators here, which gives a edge over others. Track GATE 2023 by 2020 and 2024 with Unacademy Lite subscription, which is mix of topic and subject-wise mock test. Get access to structured test series, detailed solutions and performance analysis. To subscribe, you can use the code KNR10. This Unacademy Ask a Doubt feature, which is available both on website and app. You can ask 3 doubts at a time. Just a second. And get the solution in your preferred language. It's also very easy to ask your doubt. Just click, crop and submit. Get in touch with our counselor if you are having any doubts in preparation journey, subscriptions or about latest offers. You can dial this number and get in touch with our counselor. These are special class features which includes interactive live classes, polls for the learners, raise hand option. You never miss a class when the notification is on. You can download the lecture notes then and there. You can access anytime and anywhere. These are the new batches where GATE 2024 will be started tomorrow, April 13, 2022 for electrical explained in English. Spark GATE 2023 for electrical explained in English will start tomorrow. Where GATE 2024 for ECE explained in English will start tomorrow. Spark GATE 2023 for ECE explained in English. This will also start tomorrow. We are into antennas CTQ series. Concept through question series. In this concept through question series, we are into antennas concept through question series, and where antennas is part of EMFT syllabus. In EMFT, dear, we'll have 5 modules. Module 1 is elements of EMF theory, which is common for both ECE and electrical. Already a playlist has been created on this. With 40 videos and 50 hours of content. Module 2 is EM wave propagation. And on this EM wave propagation also we have created a playlist. 15 videos, 30 hours of content. Module 3 is transmission lines. Module 4 is waveguides, where you have both rectangular and circular waveguides. Module 5 is optical fiber communication and antennas. These antennas were covered in Antennas Mahamarathon series. With 18 videos and 38 hours of content. So what we have so far is Module 1 we have 50 hours of content. Module 2 we have 30 hours of content. Module 5 we have 38 hours of content. Total of 118 hours of content is available, and I am going to add 1 or 2 hours more to this, making it a 220 hour content. Dealing for EMFT. This is what we have planned. Of which let me explain module 1. Module 1 is elements of EMF theory. It's common for EC and electrical. Elements of EMF theory is common for both EC and electrical. For electrical it is complete syllabus, for EC it is module 1. For this module we have created a playlist. With 40 videos and 50 hours of content. This is module 1, elements of EMF theory, common for EC and electrical. For EC, it is part of a syllabi. For electrical, it is a complete syllabus. A wonderful playlist with 40 videos and 50 hours of content is already designed for this. What we have done in module 1, we divide the syllabus into 3 parts. First part, basics. Second, electrostatics, or I'll write electrostatics and magnetostatics in one part. A static field theory. Later we modify it to time varying field theory. Time varying field theory, through which they will get Helmholtz equations or wave propagation. So this is a major syllabi. We divide the syllabus into 3 parts. Let us see what are the subparts in it and what is the content in these 3 parts. The first one is basics. In basics we have discussed about elements of vector calculus, second one, coordinate system. The small concept called basics is divided into elements of vector calculus and coordinate system. So let us discuss what we had covered under elements of vector calculus. Let us see what we had covered under elements of vector calculus. What they are calculated under elements of vector calculus. Good evening, Sairam. Good evening, Bhaskar. Good evening, Chakravarti. Good evening, Rohit Bhora. Good evening, dear. What we study under elements of vector calculus, dear? Pressure, voltage, current, all these are scalars. And we went for vector. Vector is one which has both magnitude and direction. Examples: displacement, velocity, acceleration. Then we went for unit vector, which gives you the direction of the vector. Then we went for addition of vectors. Addition of vectors, we went through. Parallelogram law. And what is the second law, dear? What is the second law? One is parallelogram law. What is the second law? What is the second law? One is parallelogram law, and then what is the second law? Yes, anyone? One is parallelogram law, the other is head to tail rule. Or also called as triangular law. Also called as triangular law. Then we have seen basic laws of vectors. Basic laws of vectors. And basic laws of vectors we have seen commutative law. You have commutative law of addition. A plus B is equal to B plus A. Associative law. A plus of B plus C is equal to A plus B plus C. Distributive law. K into A plus B is equal to Ka plus Kb. And for multiplication, K is a scalar, A is a vector, K into A is equal to A into K. Commutative law of multiplication. Associative law of multiplication. K is a scalar, L is a scalar, K into LA is equal to K into L into A. Distributive law of multiplication not defined. Distributive law of multiplication not defined. Then we are seeing multiplication of vectors. Under multiplication of vectors, we are seeing dot product, also called as scalar product. Is cross product or vector product. And also we had seen dot product and cross product obeys how many basic laws, which are called as CAD laws: commutative, associative and distributive laws. It's a wonderful topic, dear. Please go through the playlist. Go through this playlist. It's a wonderful topic. Seventh one, seen del operator, del and its properties. Del is again a wonderful operator called as spatial derivative operator. Del is spatial derivative operator, also called as vector differential operator. And we have seen its properties of del. Del, when associated with dot product on a given vector, gives you del dot A. This is called divergence of A. And if this divergence is 0, then A is said to be divergenceless. Also called as solenoidal field. A is solenoidal. When this divergence is positive, it is called as source. When this divergence is negative, it is called as sink. Similarly, when del operated over a vector with using a cross product, this is read as curl of A. If this curl is 0, vector A is irrotational, not equal to 0, then it is rotational. Del operated directly over a scalar gives you gradient of scalar, which results in a vector quantity. Gradient of a scalar which results in a vector quantity. These are properties of del. These are properties of del dear. Then we had seen vector identities. Vector identities are two major vector identities I am writing. Divergence of del dot, curl of any vector is 0, curl of gradient of any scalar is 0. These are vector identities. With this, we have completed elements of vector calculus dear. Very important concept in that particular series. Please go through the playlist for detailed understanding of these particular topics. Clear? Then the second part, and for static field theory, in static field theory, started with, that's the first part, sorry, 1 second here. First part of the basics is done. The second part of the basics, and for coordinate system. In coordinate system, we went for types of coordinate system. In types of coordinate system, and for Cartesian coordinate system, cylindrical coordinate system, and spherical coordinate system. Cartesian coordinate system is also called as rectangular coordinate system, Cylindrical coordinate system is also called as circular coordinate system. Here the coordinates are x, y, z. Here the coordinates are rho, phi, z. Here the coordinates are r, theta, phi. Okay, so these are the types of coordinate system. We have defined each of these coordinate. We defined its range. And also we have defined the definition for each of this coordinate. If you go for range, all x, y, z are from minus infinity to plus infinity. As for Cartesian, in cylindrical, rho is between 0 to infinity. Radius of the cylinder. Phi is azimuthal angle between 0 to 2 pi. Z is minus infinity to plus infinity. R is radius of the sphere, 0 to infinity. Theta 0 to pi. Phi 0 to 2 pi. Phi 0 to 2 pi. Is that clear? Then we had seen point transformation. How to convert a point from one coordinate system to another coordinate system. That is explained in this concept called point transformation. Then we have seen unit vector relations. What are unit vectors? In Cartesian coordinate system, unit vectors ax, ay, az. In cylindrical, a rho, a phi, az. In spherical, ar, a theta, a phi. How these unit vectors are interrelated is done in this particular topic called unit vector relations. Then we went for how to write differential length, differential surface and differential volume in all three coordinate systems. In all three coordinate systems, and also we got the shortcut for this. A single formula for DL, single formula for DS and single formula for DV, which is suitable for all three coordinate systems. Then after differential length, differential surface and differential volume, we also derived the formula for divergence, curl, gradient and Laplacian in all three coordinate systems. So this is what we have dealt under basics, which we took around 15 hours. That's why this particular playlist is a very special one, because 15 hours of time we have just spent on these basics. Total of 15 hours of time only on basics, dear. Is that clear? That's about basics. Then we went for static field theory. In static field theory, we went for electrostatics. And then magnetostatics. Under electrostatics, you have seen topics like Coulomb's law, which gives you force between point charges and their applications, or point charge, line charge, surface charge and volume charge. And Coulomb's law is called as the generalized law that governs electrostatics. Then we went for Gauss law. Gauss law, a specific law which can be applied only when you have Gaussian surfaces. And Gaussian surfaces are those which are symmetric with respect to charge distribution. We have seen applications of Gauss law or point charge, line charge, surface charge and volume charge. Besides this, we had seen topics like electric potential, relation between E and V. So these are like major topics that we have dealt under electrostatics. Similarly, under magnetostatics, we dealt with the generalized law, Biot-Savart law. It gives you magnetic field at a distant point due to current carrying element and their applications, or line current, surface current and volume current. It's a basic law that governs magnetostatics. Then we went for a special law called as Ampere's law. We've seen applications over line current, surface current and volume current. This Ampere's law is a special law which can be applied only when there is an Amperian path. An Amperian path is something which is symmetric with respect to current distribution. Just like a Gaussian surface is symmetric with respect to charge distribution, Amperian path is symmetric with respect to current distribution. And Gauss law can be applied only when there is a Gaussian surface. Ampere's law can be applied only when there is an Amperian path. And Gaussian surface is one which is symmetric with respect to charge distribution, and Amperian path is one which is symmetric with respect to current distribution. Coulomb's law is generalized law that governs electrostatics. Biot-Savart law is the generalized law that governs magnetostatics. Gauss law and Ampere's law are special laws under electrostatics and magnetostatics. In electrostatics, we define electric potential, whereas in magnetostatics, we define this electric potential is also called as EMF, electromotive force. Whereas in magnetostatics, we define scalar magnetic potential given by Vm. And vector magnetic potential given by A. Because that the scalar magnetic potential, also called as MMF, magnetomotive force, which represents current, cannot be defined in all the regions. Magnetomotive force can be defined only in the regions where there is current is zero, or the current density is zero, or the conductivity is zero. Scalar magnetic potential or MMF, magnetomotive force, can be defined only in the regions where conductivity is zero. That is in case of insulators or free space or vacuum. Only in those regions you can define scalar magnetic potential. In all the other regions, it cannot be defined. So we go for vector magnetic potential. This property that the scalar magnetic potential cannot be defined in other regions is called failure of MMF. It's called failure of MMF. And also we have seen the relation between A and B. Del cross A is equal to B. Relation between E and V, E is equal to minus del V. So that is what we have derived in static field theory. And in this, we also derived some common topics. And the common topics, we derived work done in both electric field and magnetic field. energy density, work done and energy density, both electrostatics and magnetostatic fields. We have seen Poisson's and Laplace equations. Poisson's and Laplace equations, both for electrostatics and magnetostatics. Boundary conditions. From electrostatics we derive 2 Maxwell equations, and from magnetostatics 2 more. Total 4 Maxwell equations, and in electrostatics we derive important term like capacitor and its types. This is parallel plate capacitor, coaxial cable capacitor and spherical capacitor. And also we will see types of inductors. We have solenoids and toroids. So these are the common topics we have worked on: energy density for both electrostatics and magnetostatics, Poisson's and Laplace equation for both, and boundary conditions also for both. Actually, there are 4 Maxwell equations and 4 boundary conditions. So these are the common topics here. Under static field theory, there are, from electrostatics we derive 2 Maxwell equations. From magnetostatics we derive 2 more Maxwell equations. Put together, it will become 4 Maxwell equations. Maxwell equations for static fields. Maxwell equations for static fields. Equation number 1. Closed surface integral of d dot ds is equal to volume integral of rho v dv. Clear? 1 second here. 1 second. Sorry. Sorry dear, there's small bleeding in the gum. 1 second. Okay. Fine. Maxwell equations for static fields. Closed surface integral of d dot ds is equal to volume integral of rho v dv. Integral form. Differential form del dot d is equal to rho v. So Gauss law for electrostatic fields. Second, closed loop integral of E dot dl is equal to 0. Del cross E is equal to 0. Curl of E is 0. E is irrotational vector. This is from conservative property of electric field. Conservative property of electric field. Third one. Closed loop integral of h dot dl is equal to surface integral of j dot ds. Implies del cross h is equal to j. Ampere's law. One closed surface integral of E dot ds is 0. Implies del dot b is equal to 0. Gauss law for magnetic fields, also called as non-existence of magnetic monopole. These are Maxwell equations for static fields. From this we get, solving it on a boundary, we get dielectric boundary conditions. The first of the dielectric boundary conditions is ED1 is equal to ED2, tangential component of electric field is continuous across the boundary of discontinuity. Second, dN1 is equal to dN2 if and only if rho s is equal to 0, where rho s is a surface charge density that is deliberately placed on the boundary. So dN1 is equal to dN2, normal component of electric flux density is continuous across the boundary of discontinuity if and only if rho s is equal to 0. It is conditionally continuous. Magnetic field HT2 minus HT1 is equal to K cross AN. When K is 0, this is vector rotation, scalar rotation, HT1 is equal to HT2. If and only if K is equal to 0, tangential component of magnetic field intensity is continuous across the boundary of discontinuity if and only if the surface current that is deliberately placed on the boundary is equal to 0. It is conditionally continuous. Fourth one, Bn1 is equal to Bn2. Normal component of magnetic flux density is continuous across the boundary of discontinuity. It is unconditionally continuous, and these are called dielectric boundary conditions. In dielectric conductor boundary condition or dielectric perfect conductor boundary condition, in dielectric conductor boundary condition or dielectric perfect conductor boundary condition, as we know, field cannot exist in a perfect conductor. The field will become 0. So boundary condition that you get are E tan is equal to 0. Tangential component of electric field on the surface of perfect conductor is always 0. Second one, D normal is equal to rho s. Normal component of electric flux density is equal to surface charge density. H tan is equal to K cross AN. Tangential component of magnetic field intensity, H tan is equal to K cross AN. B normal is equal to 0. These are called dielectric conductor boundary conditions. Dielectric perfect conductor boundary conditions. So this is what we are derived in the static field theory. And here we have seen types of capacitors like parallel plate capacitor, coaxial cable capacitor and cylindrical capacitor. It's in types of inductors like solenoid and toroid. These are the common topics there. This is what we have discussed, that is static field theory. The second part, elements of EMF theory. The third one is time varying field theory. Under time varying field theory, two changes will take place in Maxwell equation for static fields. Equation 1 and equation 4 will remain same. 2 and 3 are going to change. 2 is varied by Faraday's law. 3 is varied by Maxwell contribution. So two changes are: one, Faraday's law. According to Faraday's law, the induced EMF within a closed path is equal to rate of change of flux linkage. Later on, scientists Heinrich Friedrich Emil Lenz introduce a negative sign indicating that the induced EMF always opposes the flux produced it. Thereby we got V EMF is equal to minus d lambda by dt, where lambda is equal to flux linkage n into psi m, where n is number of turns. If you consider a straight conductor, n is 1, lambda is psi m, V EMF is closed loop integral of E dot dl is equal to minus d psi m by dt. Psi m is equal to surface integral of B dot ds. Closed loop integral of E dot dl is equal to surface integral of minus dou b by dou t dot ds. It's called integral form of Maxwell's second equation for time varying fields. Applying Stokes theorem on this, you get surface integral of del cross E dot ds. Closed loop integral of E dot dl is equal to surface integral of del cross E dot ds is equal to minus surface integral of dou b by dou t dot ds. Implies del cross E is equal to minus dou b by dou t. It's called the differential form of Maxwell's second equation for time varying fields. This is one change. The second change is Maxwell contribution. Are also called as inconsistency of Ampere's law. What Maxwell has proved that Ampere's law, which is del cross H is equal to J, is inconsistent. Ampere feel that current carrying can happen only when there is a conductor. But what Maxwell says is current can even fly in air. And such current which can fly in air is called displacement current. He proved this by taking divergence on both sides. Del dot del cross H is equal to del dot J. But from vector identity, divergence of curl of any vector is 0. Therefore, you get del dot J is equal to 0. But from continuity equation, del dot J is equal to minus dou rho V by dou T. And continuity equation is from conservative property of charge, which is a natural phenomena. Therefore, there is an ambiguity between these two. In order to overcome this, Maxwell has introduced a term called JD, displacement current density. Then he had done divergence on both sides. Now del dot del cross H is equal to del dot of J plus JD. But this is 0 from vector identity. Therefore del dot J plus del dot JD is equal to 0. Implies del dot JD is equal to minus del dot J. But from continuity equation, del dot J is equal to minus dou rho V by dou T. Minus of minus is plus, del dot JD is equal to plus dou rho V by dou T. Applying Gauss law, del dot JD is equal to dou by dou T of del dot D. Implies del dot JD is equal to del dot dou D by dou T. Comparing, JD is equal to dou D by dou T. From this, the modified form of Ampere's law is del cross H is equal to J plus JD, where J is conduction current density given by sigma E, which depends on conductivity of the material, and JD is called the displacement current density, which depends on time varying field. Time varying electric field. So these are the two changes that were done. These are the two changes that were done in the Maxwell equations. Any doubt? Any doubts? When we include these two equations, you get Maxwell equations for time varying fields. Equation number integral form closed surface integral of d dot ds is equal to volume integral of rho v dv. Differential form del dot d is equal to rho v source Gauss law for electric fields. Second, closed loop integral of E dot dl is equal to 0. Implies del cross E is 0, rotation of E is 0. Static electric field is irrotational, conservative nature. This is called, from the conservative property of electric field. Now this was defined for static fields, but when you write for time varying, what you write here? This is replaced by Faraday's law. Closed loop integral of E dot dl is equal to surface integral of minus dou b by dou t dot ds. Differential form del cross E is equal to minus dou b by dou t. Spatial orientation of electric field depends on time varying magnetic field. This is from Faraday's law. Third one, closed loop integral of H dot dl is equal to surface integral of j plus jd dot ds. Differential form applying Stokes on LHS del cross H is equal to j plus jd, where j is conduction current density sigma e, jd is displacement current density dou d by dou t. Again you can see the spatial orientation of magnetic field depends on time varying electric field. This is called Maxwell contribution, also called as inconsistency of Ampere's law. Inconsistency of Ampere's law. Okay. Fourth one, closed surface integral of B dot ds is equal to 0. Implies del dot B is equal to 0. Gauss law for magnetic fields. Gauss law for magnetic fields, also called as non-existence of magnetic monopole. And if you see these two modified equations here, what we get is del cross E is equal to minus dou b by dou t. Spatial orientation of electric field depends on time varying magnetic field. Del cross H is equal to j plus jd sigma E plus dou d by dou t. Spatial orientation of magnetic field depends on time varying electric field. That means both electric field and magnetic field are interdependent, which is a primary condition for these waves to be a part of a wave, because a wave is something which changes its phase with respect to space and time. The spatial orientation of field is given by beta x, beta y, beta z. Beta x gives you the spatial orientation, a change of phase with respect to space in x direction. Beta y, the change of phase with respect to space in y direction. Beta z gives you the change of phase with respect to space in z direction. Similarly, the change of phase with respect to time is given by omega t. And a wave is something where there is always interdependency between the field components. So these two equations we combine to form Helmholtz equations. Helmholtz equations. which are also called as wave equation. Then we'll understand how wave will propagate in free space, in materials with finite conductivity, in good conductors, good dielectrics, perfect dielectrics. What is the power associated with the wave? How it is polarized? How much is reflection? How much is refraction? What is reflection coefficient? What is refraction coefficient or transmission coefficient? Everything will deal in EM wave propagation. And in today's class, we have discussed about concept of elements of EMF theory. Next class, we will do problems on this. Our series is concept through questions. Today's class, I explained the concept. In the next class, antenna CTQ 8, I'll explain the questions related to these concepts. Any doubts here? Is that clear? Thank you all for joining here. Have a great day.